Hi, this is Physics Echoes. We are about to discuss how to produce an excellent IA report. In the first part of the video, we discuss how to find topic and how to meet the requirements of the criterion named exploration. This video focuses on the criterion analysis. This portion of the rubric explains the requirements of analysis. We're going to look at the expectation by taking one strand at a time. Major aspects that has to be covered under analysis are quantitative data or raw data, qualitative data, sample calculations, graph or graphs depending on the data collected, and the RQ, and finally, the interpretation of data and graphs. Let's look at strand number 1. Of course, keep in your mind, we are looking at analysis, the criterion analysis. It says the report should include sufficient, relevant, quantitative, and qualitative raw data. This data should support to derive a detailed and valid conclusion to RQ. So as the strand says, there are two sets of data to be entered. That is quantitative and qualitative data. Let's look at quantitative data, which is the raw data. The first part, it says we need to have sufficient quantitative data. So this sufficient refers to 5 or more sets of data. However, my suggestion is to go for at least 7 sets if possible. Now to design the table, go for the first column as independent variable. So this is the independent variable. The second column as the dependent variable, which is the time of fall. And you can see that the dependent variable, which is the measured quantity, we have taken 5 trials. Now, moreover, this table shows how the data table should look like. The column heading should clearly say what you are measuring, which is shown here, its unit, and the uncertainty. Please be reminded that the uncertainty is the least count or least count by 2 of the measuring instrument, depending whether the instrument is digital or analog. Another important point that you need to be careful, the data entered, which is in this example here or here, they should have the same decimal place as that of the uncertainty value. As the data is being collected, it's equally important to note down the qualitative observations. These qualitative observations shows your eye for the details. As an example, when the ball hits the surface, it's squashed. More bubbles were formed towards the sides of the vessel during the initial stages of boiling. Noting down these observations will become relevant while drawing conclusions or evaluating the method. Moving on, the strand 2 is given here. You can see that appropriate and sufficient data processing. So the strand 2 is focusing on the data processing. So after the data is collected, data processing needs to be done. So what's data processing? Basic data processing is taking the average of the data collected in various trials. By using this averaged value to determine any related constants is advanced data processing. So, in addition to averaging and calculating constants, the errors in measurements of raw data also need to be taken into consideration. So basically, there are two kinds of data processing: averaging and calculating constants from the collected data, and also the processing of errors. All these should be enabling us to come into a conclusion to the research question. So always keep in your mind to connect the qualitative observation, the interpretation of graph, everything to be connected to the research question. I'm giving an example of process data table. Of course, the first column remains the same. We are not doing anything here. The second column is the process data, which is the average time. The third column is the uncertainty in time, which can be calculated by using the equation maximum time minus minimum time divided by 2. This maximum time and minimum time are taken from those 5 trials that we have taken before, which once you do that calculation, you will come up with this number, 0.012. The final column, which is again the processed constant, is the acceleration of fall using the equation A equal to 2s by t square. Don't forget to write the unit, meter per second square. So you can see that the process data table clearly shows all relevant details. Now, right underneath the table, we need to include the sample calculations. So as an example, I have taken this height to do the sample calculation. What all will I show there? I'll show the average time calculation and the uncertainty in time. You just put in these samples, like how did you calculate a trial 1 value plus trial 2 value plus etc. divided by, since you have taken 5 trials, you will write divide by 5. And uncertainty is, use this equation, put this equation here, substitute the maximum time, minimum time, and show that calculation. And average acceleration calculation and uncertainty in acceleration. So, once we are done with the data processing, next step is to represent these data in the form of graph or graphs. It's always better to show how dependent variable changes with independent variable in a graph. Therefore, I call it as a raw data graph. In this example, it is the height versus time. Please be reminded our equation was S equal to half a t square, right? From this we got A equal to 2s over t square. This is the equation we have used. So we are going to plot a graph between S, which was the independent variable, and time, which was the dependent variable. And we are going to get, because as the distance increases, the time will also increase. Therefore, we are going to get a graph somewhat like this. This is our expected graph. So this graph is a visual representation of the data collected. Now, of course, don't forget to show the error bars of time here. Now, let's say if there are outliers, one of the time that you measured is quite far from the point or the line that you are, or the trend line. So what you can do is you can remove that outlier and draw a new graph between S and T. Now, in this, we will have only 7 points, right? 1, 2, 3, 4, 5, 6, 7. Let's say these are the points, and this is the outlier. So when I'm removing this outlier and drawing the new graph, still I'll have 6 points to see the pattern. So that is the advantage of taking 7 sets of data. Now, depending upon the experiment, you can have process data graph. So here this graph is not linear, or it's not a straight line. So in order to linearize, we are drawing a graph between height and time. So distance and time square, which we are expecting a graph like this. All right. Also, in addition to this graph, you can also have a graph between height versus acceleration. So you will have a graph between S and A. And since we know that acceleration of free fall is constant, we are expecting a straight line like this. Now, from the linearized graph, we can find the gradient. So the gradient will be, T square by S, which is delta Y over delta X. T square by S will be equal to 2 by A according to this equation. All right. Then what do? We have this equation S equal to half A T square. So this is trying to tell me that S is proportional to T square. So we are going to get a straight line passing through the origin. So we are comparing this with the equation Y equal to mx plus c. Now, when I'm comparing this, I can see that my expectation is the y-intercept should be equal to 0. However, after taking the data and plotting it, if you are getting a graph that doesn't pass through the origin, that is, if the y-intercept is not equal to 0, you should be able to identify the errors associated. So what are the requirements in a graph? Title for the graph is a must. Height versus time, that can be the title. The horizontal and vertical axis to be labeled. So when we are drawing the graph, of course, the independent variable, which is the horizontal, which goes in the horizontal axis, which is distance in this example, unit meter, and the dependent variable which goes in the y-axis, which is time, and its unit second. Don't forget to put the units. Errors of data to be shown, especially that of dependent variable. Why are we saying dependent variable? Now, we are expecting a graph of this manner. So, while we are plotting the graph, you need to compare the uncertainty of the variable that is plotted on the y-axis with the uncertainty of the variable that is plotted on the x-axis. So basically, we are comparing the uncertainties of the variables. Now, if the uncertainties of the variable that is plotted on the y-axis is much greater than the uncertainty of the variable that is not on the x-axis, then this can be ignored and we can focus only on the uncertainty of the dependent variable, which turns out to be the vertical error bar. Then equation of curve or line to be shown and correlation coefficient also to be shown. So you need to show those equation and Pearson coefficient or R-square value, which you can obtain directly by clicking on a box in the Excel. So that also should be shown. In addition to that, if the gradient or y-intercept is helping you to calculate any constant, then worst fit lines to be drawn. That is the maximum fit line and minimum fit lines to be drawn. This is applicable only if the graph that you're obtaining is a straight line, y-intercept. Moving on to strand 3. The report shows evidence of full and appropriate consideration of the impact of measurement of uncertainty on the analysis. So this strand is talking about the impact of measurement uncertainty. Here, you can discuss how the uncertainty in raw data has affected the calculated values. In certain cases, the experimentally determined constant has an accepted scientific value. In that case, compare them, and also the percentage of deviation can be calculated using the equation. Now, for example, we got A as 9.9 from the experiment. So A from the experiment. Now, A accepted, that is the scientific or literature value is 9.81. So what I can say, looking at these two values, I can say the calculated value of acceleration of free fall is 9.9, although expected value is 9.81. And the percentage of deviation is given by so and so. So the question is, how do I find the percentage of deviation? It is using the equation measured value minus absolute value divided by absolute value. So this is 9.9 minus 9.81 over 9.81. You convert it to the percentage, so multiply by 100. So that will tell you the percentage of deviation. Finally, the strand number 4. The process data is correctly interpreted. It's not only a matter of showing all these calculations. You need to interpret the data. So what should be included there? Discuss the trend line. Is it in line with the expectation of RQ? For example, how the time of fall affect the distance or the height. So you are expecting height versus time square as a straight line passing through the origin. However, let's say you got a graph or a line slightly shifted from origin 0. So maybe it has a y-intercept of 1 unit or 0.5 units. So you need to say that it is due to the systematic error and identify what was there. What was that error? Does the data or the graph help you to identify the presence of random or systematic errors? Are the outliers preventing you from getting a general trend for the exploration? And I would again insist on, don't forget to connect all this to your research question. By including all these points, which we discussed in strand 1, strand 2, strand 3, and strand 4, will help you to score the highest band for analysis criteria. So I hope the discussion was helpful for you. See you next week. Thank you.